Okay, let's spend a little bit of time setting up the finite well calculation. Okay, so we will have a potential energy that has this form. Here's the x-axis. So here's the potential energy. This will have value u naught, and this will be 0. And this is L, and this is x equals 0. Okay, so I'm going to set it up like this. Again, what does it mean? Well, it's a model. Okay, it's a model that represents some kind of a more realistic, smooth potential energy well, some sort of an attractive potential energy. So it could represent a charged particle that's attracted to some kind of a continuous charge distribution, or it could represent some sort of a other generic situation, right? We discussed that we can realize this kind of a potential energy well by placing two capacitors and bringing the capacitors closer and closer while the voltage across the capacitor remains constant. So remember, so for capacitors, right? So this would be, this is delta U equals Q times delta V. If I apply 9 volts, I get a certain potential energy that a charged particle passing through capacitors will gain or lose. If I make the voltage constant and bring the plates closer and closer together, then basically you get something that looks like that. You might say, well, it has an infinite force because it's an infinite slope. And you remember that F equals minus du dx. It has an infinite force, but it's a force that does finite amount of work, right? So, yeah, so it's a force that does a finite amount of work during infinitesimal amount of space. In contrast, an infinite potential well, it's also an infinite force, but it's an infinite force that does infinite amount of work in an infinitesimal distance. In other words, it can stop any particle, right? In contrast to this situation, well, if a particle has large enough kinetic energy, it will be able to overcome that kick of an infinite force and continue moving outside, right? So if I have an energy that looks like this, right? So this is scattering state. So a particle has a large amount of kinetic energy, and it lost most of that kinetic energy to that finite work that was done by the electric field within the capacitor. It would, if I make the capacitor, if I bring the plates of the capacitor closer and closer, it becomes an infinite field that's working over infinitesimal area, okay? And the work done by that infinite field over infinitesimal distance, sorry, distance, not area, equals to the change in the kinetic energy. So now, as the particle leaves the capacitor on the other side, we'll have a lot less kinetic energy. We'll have only this much kinetic energy left. And if I have this kind of energy, so now this is a bound state, right? So this would be a bound state. So that means, well, if the capacitors are not infinitesimally close, if they're like, if there's a finite distance between them, that means the charge will come to a stop somewhere in between the plates. And we're not going to resolve that distance, right? In other words, when the separation between capacitors is larger than the separation between the plates, we can ignore the fact that it takes some finite distance for the potential energy to change from 0 to U naught, and it basically looks like just a sharp edge. Right? So for example, L could be a meter, and we could place the two capacitors, they're like micron, their plates are micron apart, and we're not gonna worry about what happens in between the plates, just how exactly the particle stops when it's in between the plates. Okay, so you can realize this kind of a potential energy landscape with capacitors. But again, remember, the value of this is not so much that you would put a charged particle between the two capacitors and make it bounce between them. Like, why would you want to do that? Well, I don't know. The value of this thing is it's more educational value, that it's a model for many other realistic type of attractive wells, some potential energy landscapes that try to attract particle, right? So more realistic. So more realistic. So this is a model. This is really a model for more realistic scenarios like these. And like I said, the way you can realize that is you can have a charged particle that's interacting with some kind of a continuous smeared out charge distribution. So this could be some kind of a charged solid, and you could have maybe an electron moving towards that charged solid, right? So it's not a, it's a kind of a charge that's smeared out, some kind of an ionic solid or something like that. So that's what this kind of a potential energy would represent, some sort of an attractive situation. And also you can think, well, yeah, so, but really this is just kind of has more educational value. In any case, so I think I've said enough. I tried to motivate this. I'm gonna call this region 1 up until here. This I'm gonna call region 2. And this is, you know, from minus infinity to 0 is region 1, from 0 to L is region 2, and from L to infinity is region 3. Okay, so again, region 1, minus infinity to 0, region 2, 0 to L, and region from L to infinity. Okay. You might say, why do you make curly brackets here and square brackets here? Because infinity is, you know, if you want to be fastidious, it's not that important. You can never reach infinity. It's kind of an open, it's an open. I guess you could say it's an open set, but anyway, don't worry. From minus infinity to 0, from 0 to L, and from L, sorry, and from L to infinity. So this should say L to infinity. Okay. Okay. So note that here, so we are going to solve a bound state problem, meaning E is less than U naught. So the way I set it up, it means that E energy will be less than U naught. Okay, so I realized in the previous video something got erased, and then I realized it got erased because I probably moved my hand. Anyway, it's the perks of doing this kind of thing. So here, E is less than U, right? Here E is less than U because U equals U naught, bigger than E. Here E is bigger than U, which equals to 0, and E is less than U again. That will be important. Okay. Let's look at region 3. So, sorry, region 2. Region 2. So Schrodinger's equation in region 2 is the good old free particle Schrodinger's equation because U is 0, right? So remember Schrodinger's equation minus h bar squared over 2m squared psi dx squared plus U psi equals E psi. Okay, so in region 2, u equals 0. So Schrodinger's equation is minus h bar squared over 2m. Second derivative of psi dx squared equals e psi, which I can write like this. Okay, so this is a bunch of positive number. And let me write it like minus k squared psi, okay, in anticipation, where k squared equals 2m e h bar squared is bigger than 0. Okay, it's bigger than 0, so that's why I can call it k squared. Okay, so you can see that d squared psi dx squared is proportional to psi. And what kind of a function when you take, sorry, it's proportional to minus psi. So can you think of a function that when you take its two derivatives, it returns you something that's proportional to that function with a minus sign? Well, there are two possibilities, sine or cosine. Okay, and in general, you can have a linear combination of both of this, of both of those. So general solution is psi in region 2 equals a sine kx plus b cosine kx. I had a question at office hours. Why is that? Just take two derivatives of this, and you will see that you will get the function back multiplied by minus k squared. Just try it. Okay. Okay, so this is general solution in region 2. You might say, what are these a and b? Well, at this point, they're undefined constant, and we will have to fix those constants by applying boundary conditions. We will do that. How about in region, we will do that, but first let's do region 1. In region 1, Schrodinger's equation reads minus h bar squared over 2m d squared psi dx squared plus u naught psi equals e psi, or d squared psi dx squared equals u naught minus e times 2m h bar squared times psi. So now the second derivative of psi is proportional to plus psi, because this is now bigger than 0. This whole thing right here is bigger than 0. Right, so it's proportional to plus psi. So sine and cosine will not be a solution. Because if sine is a solution, then you take two derivatives, it brings a minus sign. Cosine is a solution, you take two derivatives, it again brings a minus sign. Okay, so now let me call this k squared psi dx squared equals kappa. This is not k, this is kappa squared psi. So this is kappa. To distinguish k in region 2 from kappa in region 1 or region 3. Okay, and so now general solution, so this is bigger than 0. So before we had a minus sign, minus times some positive k squared times psi. Now it's just positive kappa squared. So for example, this could be d squared psi dx squared equals minus 17 times psi. Now is d squared psi dx squared equals 17 times psi. And that affects things. So general solution will be psi in region 1 we'll have some coefficient times e to the kappa x plus some other coefficient e to the minus kappa x. Again, these are undetermined coefficients. Again, if you don't believe me, just try it. Just take two derivatives of this, and you will see that you will get psi back with a kappa squared in front. Okay? And region 3, it's exactly the same thing. So same Schrödinger's equation. And so now the general solution in region 3 will be, but it's a separate solution. So in general, we cannot assume that it will have the same coefficient. So it's e to the kappa x plus f to the e minus kappa x. Okay. So let's summarize what we have. We have x. So here's region 1, region 2, and region 3. I'm going to plot the potential energy landscape. And I guess this is psi. So here psi equals c to the kappa x plus d to the minus kappa x. Here psi equals a cosine kx plus b sine kx. And in region 3 equals e to the kappa x plus f to the minus kappa x. Okay. So basically, it means it's some kind of a sine and cos. It means it's some kind of a combination of growing and decaying exponential, right? So it's basically this plus this. Here it's some kind of a sum of sines and cosines, and here again it's growing plus decaying exponential. Okay, that's what's going on. So now we have to start applying boundary conditions. How many boundary conditions do we need? Well, how many coefficients do we have? We have 1, 2, 3, 4, 5, 6. So 6 unknown coefficients. So we need some kind of 6 equations or 6 conditions. Okay, so we need 6 equations, conditions. Where do we get those 6 conditions? Well, from boundary conditions. What are the boundary conditions? Psi must be continuous at x equals 0 and x equals L. So basically, we're going to try to stitch these pieces together in such a way that there is no discontinuity in the wave function, and that also there is no discontinuity in the slope. So psi must be continuous at x equals L and x equals 0. So that's 2 conditions. One at x equals 0, the other is x equals L, continuity. And then d psi dx must be continuous at x equals 0 and x equals L. Remember, this was relaxed, this condition was allowed to go when we had infinite dwell. You can actually show that from this studying the mathematical properties of the Schrödinger's equation. And I said, just trust me. But now, because it's a finite barrier, in general, the derivative must also be smooth. So, okay, so we have 4 conditions. We need 6. But we also know that the psi must be normalizable. What does that mean, normalizable? Well, basically, the integral of psi squared of x dx must be, it must be some number. If it's number, we can multiply by 1 over that number to make it a 1. And you can see that these guys right here just won't cut the mustard, because if you have a decaying exponential on the left, it will pick up infinite area, and this one will pick up infinite area. Okay, so that means that d equals 0, and e equals 0. Okay, so these are sort of the additional 2 conditions, right? So this is 2 conditions. We cannot have this infinite bits here. We cannot have this bit because it contains infinite area between minus infinity and x equals 0. And we cannot have this bit because it contains infinite area between 0 and x plus infinity. So we must eliminate these bits. So now what we have, you can start seeing what the wave function will do. It will have this bit, we've eliminated the other bit. Then you will have some sort of a oscillation, and then something like that. So the wave function will look something like this. This is not detailed, it's just a qualitative picture. It starts at 0 at x equals minus infinity, it grows, it reaches the classically allowed region. In that region, the wave function is oscillating wave function. And then in region 3, again, classically forbidden region, the wave function goes to 0. And you can probably guess that as the barrier height is increased, as we go to the infinite barrier depth, the wave function will decay faster and faster, right? And so this is larger U naught. This is smaller U naught. You can guess that because we have to pass over into the infinite barrier regime, right? So we still have to, we applied 2 conditions. We still have to actually go ahead and apply these conditions in order to find the remaining coefficients, right? So we've eliminated this bit. We said d and e to 0. We have c, a, b, and f. We have 4 remaining constants and 4 remaining equations. And so now we have to apply those boundary conditions. Okay, so so to stitch the 3 pieces, psi 1, psi 2, and psi 3 at x equals 0 and x equals L by finding C, A, B, and F. C, A, B, and F from applying the remaining 4 conditions: smoothness of psi and the derivative at x equals 0 and x equals L. This probably sounds very dry and mundane to some of you. And yes, you might maybe see it that way, but I just wanted to show you an example of what a real calculation looks like. We'll just grind through it, and then we will see that quantization will again pop out of this. So quantization comes from applying boundary conditions. And we will find that some kind of a formula for energy levels inside the well, and then we will digest it. We will reflect on it, just like we did with an infinite well. We will find some properties that there's always at least one level, but there's not an infinite number of energy levels. And then the wave functions change properties depending on the energy and so on. So think of this as just an example of a quantum mechanical calculation.